Okay, let's move on to probably the most complicated example that we'll talk about, and that is a simply supported beam with a distributed load that changes magnitude from one side to the other. So, in other words, we have a distributed load that starts with a magnitude of 0 on the left here, and a maximum magnitude of W on the right. And again, this W is defined in kips per foot. Occasionally in beam tables, you will see that they define this distributed load with an equivalent point load of W, and that W, capital W, will be given in terms of kips, and it will be equal to WL over 2. Personally, I find this way of doing things a little bit confusing. When I see a distributed load, I want to define all of my formulas according to that maximum distributed load. I just find that a lot easier to think about, and also it's less steps when you start to actually analyze a beam. So, for example, this type of analysis might be used in a snowdrift situation, where we may start with 0 snow on the left here, and then that snow pile accumulates as the wind blows in this direction and piles up against, say, a wall here on this side, or a parapet. So this type of analysis is very often seen with snowdrift calculations. And when we do snowdrift calculations, we calculate this maximum W, lowercase w, in kips per foot. So personally, I think it's a lot easier to keep things in terms of that. But just note that when you look at beam tables, you may see this capital W, and you may see things like reactions and maximum moments and maximum shear forces in terms of this capital W. So just know that capital W is equal to lowercase w times L over 2. So, starting with a shear force of 0. Then we jump up by lowercase w L over 6. And now our applied loads are pointing downward, and they are increasing as we move to the right. So this time, our shear force is going to be pushed downward, but not at a linear rate. Now it's going to be pushed downward at an increasing rate, increasingly negative, until we reach the right side, where we jump up by a magnitude of WL over 3. So just to make sure that we did the calculation of our reactions correctly, if we start on the right with WL over 6, and then we decrease by the area under our load diagram, we get 1/2 times W times L. And this equals WL over 6 minus 3 WL over 6. And so we end up with negative 2 WL over 6, which is equal to negative WL over 3, which is exactly what we have. And so this reaction on the right is our maximum shear. And this is our shear curve. Now with moment, we're going to start at 0, and our area under the shear curve is positive, but the rate at which it's increasing is decreasing as we move to the right. And so we end up with this kind of funky looking shape. And we won't get into the specifics of what we would call this shape. Instead, we'll just look at what our maximum moment is here. And note that this maximum moment is no longer occurring at midspan, but some other distance. And that distance is going to be L over the root of 3. Now we need to calculate the area under this parabola. That may sound complicated at first, but the formula for area under a parabola is actually quite simple. It's very similar to the area under a triangle, except instead of 1/2, we are now taking 2/3. And so our maximum moment is equal to 2/3 the height, WL/6, times the length, L over the square root of 3. And so our maximum moment becomes WL² over 9 times the square root of 3. WL² over 9 square root 3 for our maximum moment. And so that is our shear and moment diagram for a simply supported beam with a load increasing from one end to the other. Now let's move on to our final two examples, which should be a bit easier, but they do have a bit of a twist. And yeah, that was a bad pun. So with the previous diagrams, we haven't really cared which end we started drawing our shear diagram from. But for these two examples, since we have an external moment reaction, it does matter. So for these examples, we actually want to start with our applied load on the right, which will push our shear diagram down by a magnitude of P. Then we continue on to the left until we reach the left side where our shear diagram jumps up by our reaction Ry1 equal to P, and so we end up back at 0. Now we can begin drawing our moment diagram. Again, we'll start at the right side, where we should be at 0, because this is a free end. And the magnitude of our moment will increase, though it will be negative, until we reach the left side here, where we have our moment reaction. And this moment reaction is acting in the counterclockwise direction, and so it will be positive. And so it will push the moment diagram back to 0. And this moment is equal to negative P times L. And the magnitude of our maximum moment is equal to our reaction moment, which is P times L. Now with our final example, again we'll start on the right side here at 0, and the magnitude of our shear is increasing linearly until we reach the right side, where it jumps back up by our reaction of W times L. Then with our moment diagram, from the right side, we have this free end, and our moment and the magnitude of our moment is going to increase at an increasing rate until we reach the left side. And that maximum moment should be equal to the area under this shear curve, which is 1/2 W times L, which is equal to negative WL² over 2, which is our reaction. So again, we jump up to 0. So the magnitude of our maximum moment is WL² over 2. So now we have a variety of bending and shear diagrams defined, with maximum internal shear and maximum internal moment defined. And these formulas we will use to calculate demand based on given loading. There are also a variety of other beam formulas and shear and moment diagrams defined in NDS Design Guide number 6, which I will be posting to our readings for week 3. This will be a helpful guide for you when doing assignments for this course as well as studying for the ARE. In the next video, we will start to talk about the actual stresses that occur in the member due to shear and bending.